Welcome students to the MOOCs series of lectures on statistical inference. This is lecture number 14. In the last two lectures, we have been discussing properties of an estimators. In particular, we have seen two properties, unbiasedness and of course, consistency. Towards the end of the last class, I was discussing what is called efficiency. An estimator having the minimum variance that is among all possible estimators, if the variance is minimum, then it is called the most efficient estimator. In fact, if T is the most efficient estimator, then variance, then the efficiency of another estimator is defined as variance of T e divided by variance of T. So, let me call it T, or in other words, if T is any estimator, then its efficiency is measured by comparing its variance with the minimum variance estimator. Obviously, this is less than equal to 1. It is 1 if we are looking at some estimator T whose variance is equal to T, variance of whose variance is equal to the variance of T e. Otherwise, it is more than the variance of T e, and therefore, this value has to be less than 1. The question is how to find the minimum variance estimator. This is very important, as there is no dearth of estimators, right. We have already seen that there can be any number of estimator for estimating a particular parameter theta, but the problem is how do we know this is going to be the minimum variance. The advantage thereby is that if we know that the minimum variance has to be some particular value, say v, and if we get an estimator T whose variance is same as v, then we know that it is the minimum variance estimator. In this respect, we mentioned Cramer Cramer-Rao inequality. This is not for all the classes of estimators. This is applicable to a restricted class of estimator, but still it is very, very useful for statistical inference. The CR inequality or Cramer-Rao inequality, it states that if T is an unbiased estimator. So, this is very important. We are looking at within the class of unbiased estimators. For theta, then variance of T is greater than equal to 1 upon expected value of del theta log of L whole square. More generally, if T is unbiased for g theta, which is a function of the parameter theta, and we want to estimate g theta, then variance of T is greater than equal to g prime theta square upon the same quantity, which is expected value of del theta log L whole square. In this respect, what is L? L is the joint PDF of the sample x1, x2, xn, or in other words, we want to estimate theta or some function of it. We have taken a sample x1, x2, xn. We are looking at the joint density function of x1, x2, xn, which we call L. Of course, L depends upon theta. So, in some books you may find L theta x1, x2, xn. In this class, sometimes I will be using L theta only, because it is understood that it is based upon the sample x1, x2, xn. Now, what is L theta or L theta of x1, x2, xn? It is joint PDF of x1, x2, xn, and if the underlying PDF is f theta, because this is the PDF that involves theta, then L theta is equal to f theta of x1, x2, xn, and if they are independent, then we can write it as product of f theta of xi I is equal to 1 to n. So, do not get confused with this L theta, it is something that we know very well. Since the samples are independent, most often we will be assuming this form, that L theta is equal to the product of the individual density of the sample x1, x2 and xn, the quantity expected value of del theta of log L whole square is called the information about theta that we can obtain from the sample and this name is being given by R. A. Fisher. Okay. Now, as I mentioned earlier that the Cramer-Rao lower bound is satisfied under certain conditions which are called regularity conditions. Note that theta, the parameter to be estimated belongs to some open interval theta on the real line. Theta is a non-degenerate interval. That means, theta has to be of the form a to b, a not equal to b, so that differentiation with respect to theta makes sense. The derivative of the likelihood function exists almost for all x 1 x 2 x n. If at all there is an exception, that means if it does not exist on some interval, if there exists such an interval, then that has to be independent of theta. Three, expected value of del theta log of f theta of x 1 x 2 x n whole square exists and greater than 0 for all theta belonging to theta. Because we know in the Cramer-Rao bound this comes in the denominator. So, if it is not defined or if it is equal to 0, then that term is not valid. Therefore, this has to be one of the constraints. Del del theta of f theta of x 1 x 2 x n d x is equal to del del theta of f theta x 1 x 2 x n d x. Now, you may ask what is this notation and what is A. So, A is the set on which the PDF f is greater than 0, or in other words, we are looking at only the region on which the probability density function is greater than 0. And what is dx? It is basically dx1, dx2, dxn. Say for example, here I am integrating f theta x1 x2 xn, and to be mathematically precise, I have to integrate it with respect to x1, then with respect to x2 and with respect to xn. So, it is basically an invariable integration. To keep it notationally simpler, I am using that notation dx with a tilde, which actually means this quantity. And number 5 is del del theta of the estimated t f theta x 1 x 2 x n dx is equal to integration of So, if you look at 4 and 5, you can see that basically we are allowing the differentiation to move into the integral sign, and this is possible if this limit of integration does not depend upon theta. Okay? With this assumption, now let us prove the Cramer-Rao bound, that is proof that variance of t is greater than equal to g prime theta whole square upon expected value of del del theta log f theta of x 1 x 2 x n whole square. Note here logarithm is with respect to e, and also note t is unbiased for g theta. Okay. So, we begin the proof in the following way. We know integration over a of f theta x 1 x 2 x n dx. That means, I am looking at the joint density function and I am integrating it over the entire possible range, and that has to be equal to 1, because the total probability is 1. Therefore, del theta over A of f theta x 1 x 2 x n dx is equal to, now I am differentiating this with respect to theta, and this is going to be 0. Now, by the regularity condition, the differentiation under integration, we can write it as follows. Or we can write it as so, this is the first finding A. I will come back to it later. Now, integration of del theta of L theta dx is equal to 0. So, let me write it as integration of 1 by L theta del theta L theta into L theta dx is equal to 0. I am dividing and multiplying by L theta, and since I am considering the range where L theta is greater than 0, this makes sense. Because if we differentiate log of L theta with respect to theta and taking the partial derivative, then what we are getting? This is 1 upon L theta into del theta of log L. So, this entire quantity I can write it as this, and that we are multiplying by L theta of x 1 x 2 x n and integrating. So, what is this? It is a function of x 1 x 2 x n, because this L theta is L theta of x 1 x 2 x n. Therefore, this whole quantity is nothing but expected value of del theta of log of L theta. And just now we observed that this is equal to 0. So, this is our finding 1. Again, since T is an unbiased estimator for g theta, integration over a T of L theta, let me write it with x 1 x 2 x n, but as we have seen, I am often leaving out this part if the notation is understood. Dx is equal to g theta, because that is the expectation of t. Now, differentiating it with respect to theta, we get I am leaving out this. Now, by regularity condition, we can push it inside. or as before we divide and multiply by L theta. So, I have multiplied and divided by L theta, or integration over A del theta of log of L theta into L theta is equal to g prime theta, or this is expected value of T del theta log of L theta, this is equal to g prime theta. So, if you look at in one we have got expected value of del theta log theta is equal to 0, and here we have got expected value of t into del theta log theta is equal to g prime theta. Let me call it equation 2. Now, we know that covariance, we know that the correlation coefficient between two variables x and y, which we called rho x y, is such that rho square x y is less than equal to 1. That is because the mod value of rho x y has to be less than equal to 1. Now, what is rho? Rho is equal to covariance of x y upon root over variance of x and variance of y. Therefore, covariance of x y square is less than equal to variance of x into variance of y, and this is true for any two random variables. X and y. Therefore, we can write that covariance between t and del theta of log L theta is less than equal to variance of t into variance of del theta of log L. Square. Now, covariance between t and del theta log L theta can be written as expected value of t times del theta log L theta minus expected value of t into expected value of del theta log L theta. This, as we have seen, is equal to 0. Therefore, this quantity is 0. Therefore, we are left with covariance between t and del del theta log L theta is equal to expected value of t del del theta log L theta, and which we have found that expected value of t del del theta log L theta is equal to g prime theta. Therefore, this is equal to g prime theta. Now, let us look at this. Let me call it 3. Therefore, by putting the value g prime theta here, we get g prime theta square is less than equal to variance of t into variance of del del theta log L theta, or variance of t is less than equal to g prime theta whole square upon variance of del del theta log L theta. Let us call it 4. Sorry, I made a mistake there. Variance of t has to be greater than equal to this quantity. Now, in 4, let us look at what is variance of del del theta log L theta is equal to expected value of del del theta log L theta whole square minus expected value of del del theta log L square, and this is equal to 0 from 1. Therefore, variance of del del theta log L theta is equal to expected value of del del theta log L theta whole square. Putting this in 4, from 4 which is variance of t is greater than equal to g prime theta whole square upon variance of del del theta log L theta, we can write it as variance of t is greater than equal to g prime theta whole square upon expected value of del del theta log of L theta whole square. So, this is the result that we were trying to prove, that variance of t has to be greater than equal to this, where this is called the I theta. Now, this quantity expected value of del del theta log L theta whole square is often difficult to calculate. Hence, I give some simpler form. suppose x 1, x 2, x n are I D. That means they are independent and identically distributed. Therefore, what is L theta of x 1, x 2, x n? This is equal to f theta of x 1, x 2, x n, which is the joint PDF of the sample values. Since these are independent, we can write this as f theta of x 1 into f theta of x 2 into f theta of x n. Therefore, log of L theta is equal to log of the product. And since log of product is equal to sum of the logs, this is same as sigma I is equal to 1 to n log of f theta x I. Therefore, expected value of del theta log L theta whole square is equal to expected value of del theta of sigma log of f x I is equal to 1 to n whole square is equal to expected value of del theta of log of f theta x 1 plus del theta of log of f theta of x 2 plus del theta of log of f theta of x n whole square. So, now you understand the difficulty, it becomes the sum of n terms whole square. So, this we are writing as expected value of sigma I is equal to 1 to n del theta of log of f theta of x I whole square, because I am collecting the individual square terms, plus sigma over I not equal to j del theta of log of f theta x I into del theta of log of f theta x j, and I am looking at expectation of that one. Bringing the expectation because of linearity of expectation, this is equal to sigma I is equal to 1 to n expected value of del theta of log of f theta x I whole square plus sigma I not equal to j expected value of del theta log of f theta of x I into del theta of log of f theta of x j I not equal to j. Now, note that all x i's are identically distributed. Therefore, this term is same for all I. Therefore, this particular term boils down to sigma I is equal to 1 to n expected value of del theta of log of f theta of x square plus, let us consider this part, it is expected value of two terms, the product of two terms, one is based on x I, other is based on x j, and x I and x j are independent. Therefore, the covariance between them has to be 0, and also we have seen that expected value of this is 0, because even for the greater thing, the L we have found that expected value of del del theta log L is equal to 0. By the same technique, we can find out that expectation of del del theta log of f theta x I is equal to 0. Therefore, what we find that this is the product of two terms which are independent. Therefore, their covariance is 0. Moreover, their individual expectation is 0, and therefore, since covariance of x y is equal to expected value of x y minus expected value of x into expected value of y, in this case we find this is 0, this is 0, therefore, expected value of x y is also going to be 0, or in other words, expected value of del del theta log f x y multiplied by del del theta log f of x j, this is going to be 0 for each pair I j, I not equal to j. Therefore, I make it 0. I hope that you understood the logic. Therefore, what we find that expected value of del del theta of log L whole square is actually this term, which is nothing but n times expected value of del del theta log of f x square. So, this is another interesting form of I theta. In solving problems, instead of using this, we may often use this as the denominator of the right hand side of the lower bound, or right hand side of the Cramer-Rao inequality. Now, let me discuss another form for I theta. We know that expected value of del del theta log L is equal to 0. We have already seen that. Now, consider expected value of let us try to compute this. What is this? Let us consider the product del del theta log L and L, and let us consider its partial derivative with respect to theta. We know that these are also dependent on theta. By rule of multiplication for derivatives, we can write it as del del theta of del del theta log L theta times L theta plus del del theta log L theta into all right. This is very straightforward because it is first function, derivative of first function into second function plus first function into derivative of second function. This we can write as del 2 del square del theta square of, this we can write as del square del theta square of log L theta times L theta plus del del theta of log L theta times del del theta of L theta. Therefore, del square del theta square log of L theta into L theta is equal to del del theta of log L to L theta minus del del theta of log L theta into del del theta of L. We started with this and we have obtained this, and therefore, what we are getting is del square del theta square log L theta is equal to del del theta of del del theta log L theta multiplied by L theta minus del del theta log L theta into del del theta of L is equal to del del theta of del del theta log L theta into L theta minus del del theta of log L theta into 1 by L theta into del del theta log of L into L theta is equal to del del theta of del del theta log L theta into L theta minus del del theta of log L theta, and this we can write is that we have already seen that it is del del theta of log of L theta into L theta, or del square del theta square log of L theta into L theta can be written as del del theta log L whole square into L theta. This is coming because it is the same term. So, it is square of del del theta log L theta square. Therefore, on integrating both sides, we have expected value of del square del theta square log of L theta is equal to del theta of expected value of del theta of log L. I am integrating with respect to the PDF, therefore, I get expected value of that one minus expected value of del theta log L whole square. Since we know expected value of del theta of log L is equal to 0, this we have found before, this part is going to be 0. Therefore, we can see that expected value of del theta log L whole square is equal to minus of this thing, expected value of del theta log L square is equal to minus of expected value of del 2 del theta square log of L theta. And we know that this is the I theta. Hence, we get another expression for I theta, which is this minus of expected value of del theta square log of L theta. So, we have got three different forms, one from the actual proof, but from there we have derived two different forms. One is this one and the other one is n into expected value of del theta log f whole square. So, in problem solving we shall be using one of these forms and we will be able to solve certain problems. So, in the next class I will solve a few problems using Cramer-Rao inequality and show that how we obtain the lower bound in certain cases when we are dealing with the unbiased estimators for a function g theta of the parameter theta. Okay, students, thank you. Seeing you in the next class. Thanks.